Okay, welcome to the class, and we will be talking about scrambling code generator and transport block calculation. So we have covered scrambling, but we have not told like how this scrambling code is generated. So we'll continue to do that in this class, and then this is basically the topic which we are going to see today. Okay. Now, before we get into it, what is scrambling? We see this transceiver chain, okay, the PDSCH transceiver chain. So we have this basically this complete transceiver chain. The bits are scrambled, then they are modulated. Okay, right? The scrambling is happening at the concatenated code block level. Now, so what we are considering here is basically you take a block of G rate match bits. The total number of rate match bits is G, and they are denoted as B. Okay, so B, and then it goes up to G minus 1. So now the scrambled bits, if you recall, they are basically generated as, how are they generated? You take this, the input bit sequence B of I, and then we scramble it with this code C of I, okay, right? And this code C of I is of length again G, okay, because you do the bit level scrambling. And so this is basically what it is. This is XORing of the input bit sequence and this code, okay, scrambling code, okay. Right, so this is C of I is a pseudo-random sequence. Pseudo-random sequence basically it's a random sequence, but you exactly know what is sequence. Okay, so now you not only need this code at the transmitter, but you exactly need to know this code at the receiver also, because how are you going to descramble these bits? You are going to look at this. You are going to get this scrambled sequence. Okay, right, and then you are again going to scramble it with the same sequence, C of I. Okay, this is a scrambled sequence. This is the code with which you scrambled at the transmitter. Okay, now what is this B tilde of I? B tilde of I is this B of I scrambled with C of I. You just substitute it over here, and what you get is, okay. So if you scramble a sequence with itself, what you get is a string of zeros. Okay, 0 XOR with 0 is 0, 1 XOR with 1 is 0. Okay. And now, so this will be all 0 sequence of length G, and then you do the bitwise XORing with this B of I. What are you going to get? You're going to get back the same sequence. Okay, right? Any sequence XOR, any bit XOR with 0 is the same bit. 1 XOR with 0 is 1, 0 XOR with 0 is 0. Okay, right? So you get back this. So get back the same unscrambled sequence. So this is the principle of scrambling, and this is the principle of descrambling. This happens at the transmitter, this happens at the receiver. Okay. Now the idea of this class is to learn how this pseudo-random sequence is generated. Okay, and the pseudo-random sequence in 5G is defined by a length 31 gold sequence. It will become clear what is this length 31. Okay, so you look at this. This is basically, why are we calling it as a length 31? There is a 31-bit shift register. Okay, right? And now this is what we are interested in, C of n. Okay, this is what we XORed with at the transmitter. It gave us the scrambled sequence, and then we use this sequence again at the receiver, unscramble the bit. So this is the sequence, and if you look at it, how is it being generated? This length 31 gold sequence, C of n is equal to x of n XOR with x2 of n. Okay, and this 31 is, as I said, is this 31 depth shift register. Okay, so now how is this being generated? As I said, this output sequence C of n of length G, it is generated where n is the running index. You have to generate these many bits, okay, of C of n. How is this generated? X of C of n XOR with C of n is x1 of n XOR with x2 of n. Now, in order to generate this x1 of n, okay, you have to basically initialize this shift register with some values. Okay, correct? Because what is happening here, I'll give you the exact formula later, but you see this certain bits are getting XORed, right? This is, you denote, this is, if this is x1 of 0, this is 1, 2, 3. Okay, x1 of 0 is getting XORed with x1 of 3. Similarly here, x1 of 0 is getting XORed with 1, 2 and 3. Now we need to initialize these bits with certain values. Okay, then only you can start generating this sequence. Okay, right. So now this first sequence x1 of n, how is this initialized? This is initialized as x1 of n, so n is equal to 0 is 1, okay, this bit is 1 and all other bits are 0, okay. From 0 to 30 is basically you have this one, and this x1 of n is all zeros, okay, right. So now similarly this second sequence x2 of n, how is this initialized? Okay, this is initialized by writing a constant c init in binary form, okay. So there is some constant c init which is basically given it to you in a binary form, okay. So what is the c init? The c init is basically determined based on the cell identity and RNTI, okay, radio network temporary identifier. Okay, there is an identity which is given to the user, okay, on entering the network. Okay, so it is a function of where the user is, okay, and its identity. Okay, it's a function of that. Okay, now you look at it. So the c init. Just for example, it is 250. It could be any value. I have taken it as 255. And now, so what will the second sequence be? Second sequence x2 of n will be, if you look at it, it will be basically x2 of n will be 1, okay, right, for all, and then up to n less than 7 it will be all ones, and after that it will be 0. Fine, so this is how this will be initialized, okay. Now what is happening here is, so you have initialized these two shift registers, okay. So how is it now, how x1 of n and x2 of n, how they are initialized, how they are generated for different values of n, okay, right, because you need to run this, you need to generate the c of n for n running from 0 to g minus of 1. You need to generate such a bit sequence, okay, right. So see this, what's happening here? C of n is x1 of n XORed with x2 of n, okay, right. But how is it, what is x1 of n equal to? Look at this, x1 of n plus 31 is equal to x1 of n plus 3 XORed with x1 of n. What is this x1 n plus 31? It is basically, you take these values, okay, XOR them, and then write into this last register, correct? So what is happening? This is, now you write into this, and then all this shift register gets pushed towards the right, okay, right? So you keep doing that, okay, right? So now so this, any register runs on a clock, okay, they are memory elements, and what are we doing? We are storing certain values in these memory, okay. So initially we stored certain values in this memory, in both these memories. Now we are regenerating the new values in the memory, and how are they being done? Using this formula, okay, correct. So this value gets overwritten here, okay, right, by this value, x1 of n plus, okay, and this value gets pushed here. Okay. This value, basically you will override this, you'll push these values and then write this value over here, okay, correct. So similarly you do it over here, and you look at this x2 n plus 31, what is happening? X2 of n, n plus 1, n plus 2 and n plus 3. You take these values, XOR them, okay, push it, and then basically write the new value generated over here, okay, right, and then basically the old values get lost, the new value gets overwritten over here, gets written over here, overwritten, because you are pushing it. So that's how you generate this, okay. Now what happens is, this is, if you look at it, okay, this is like a filter, okay. So this filter, every filter, if you understand basic signal processing, has a transient response, okay, wherein the filter is not stabilized. So what happens here is that what standard does is, okay, that it basically rejects the first 1600 samples, okay, which are generated using this formula, okay. Why? Because this you could consider as a transient response of the filter, wherein the filter is not stable and the values which are being generated are not random enough, okay. So the actual sequence which is used to scramble, okay, the input bit sequence is C dash of n. If you look at it, this is C of n plus 1600, okay, right. So you leave 1600 values, and the values which you get after that, you use that for scrambling the input sequence, okay. So this is basically how we generate this C of n. Okay, and this is length 31 gold sequence because it has excellent random property. The sequence which you get is basically has good properties related to the random sequence. Okay, right. So this is how it is generated in the standard. This was one thing which I had not taught you while discussing the scrambler. So this is what is left, what was left, and we have covered now. Okay. Now the second thing which was left was the transport block size calculation. Okay. And whenever we spoke about PDSCH, we assumed that the MAC layer gives some transport block to the physical layer, which it basically does, on which it does the complete physical layer processing. Okay. Now we never discussed how this transport size is calculated. Okay. And I'll show you explicitly today in the class that it is a function of the number of resources allocated to the user, its modulation scheme. Okay, right? Because if the number of resources allocated to a user is small, modulations this transport block size will accordingly be small. Okay, right? And then second case is if it is like the modulation order is larger. Okay, for the same resources, number of resources, the transport block size will be accordingly larger because you can transport larger number of bits. Okay. So we'll see this explicitly when we do this, calculate the transport size. Okay. And it needs to be calculated by both base station and user. Okay. And how it is done, so you look at it, now we understand, okay, that this, what is this first block, okay, is basically how many resource blocks are allocated to a user. Okay. And over how much transmission duration? Transmission duration is over how many symbols. Okay. Right. So that will tell us how many resource elements can be there for a particular user. Okay. Right. So this is, you see this is one variable which is there. Okay. Now other variable which is going to decide the transport block size is the MCS field. Okay. And what will this MCS table tell us? Okay. That what is the code rate? Okay. And what is the modulation order? Okay. Plus, so I spoke about the modulation order just now, and this code rate also decides the transport block size, because higher the code rate, right, you can transmit larger number of bits. Higher the code rate essentially means that you will have to append lower number of parity bits. Okay, right? So depending on, if the lower the code rate, you will have to, the physical layer will have to generate larger number of parity bits. Okay, accordingly, the transport block size will be smaller. Okay. Then there is this number of layers. Number of layers is basically number of data streams you can transmit in parallel. Okay. At this stage, we have not covered MIMO. Okay. So we don't really know what number of layers are, but it is enough to know that the standard defines the number of layers as the number of data streams which can be transmitted in parallel on each resource block. Okay. So if number of layer is 1, you can transmit only like one symbol on one resource block, on one resource element. But if the number of layer is 2, you can transmit using multi-antenna transmission, you can transmit 2 symbols in parallel on the same resource element. Okay. So if number of layer is 1, and when the number of layer is 2, you can in principle transmit twice the amount of data when compared with number of layer is 1. Okay. So these are the factors which play a role in deciding the transport block size. Okay, right? And then there is this, you take these parameters and decide something called intermediate number of bits. Okay, and then you pass these bits to a quantizer which will output the transport block size. Now what is the function of this quantizer? I'll tell you. Okay, as and when we reach here, the job of this quantizer will become immediately clear to us. Okay. So now what are we saying here? Okay. So UE can, base station and UE can calculate it from, so this information of course base station has. Okay. And what are we saying? That UE can calculate it from the PDCCH, which will provide this, all this above information. Okay. So what are we saying? That same information needs to be sent to the user also, so that it can calculate the transport block size. Okay, right? So the same formula which is used at the base station has to be used at the UE side also to calculate the transport block size. Okay. So now what is the job of quantizer? Quantizer ensures that the final transport block size is basically byte aligned code block. Okay. So what is it saying, that basically this one of the job, okay, is whatever is ensured, this quantizer ensures that the code blocks which are generated, okay, after segmentation, they are like byte aligned. Okay. So that the processing becomes easier. Okay, if you're, and then that's where I'll stop, that it is basically the processing of this byte aligned code block become easier. Okay, right? And how does it help? It basically helps in this byte aligned code blocks. They help in they ease the LDPC processing. Okay, they help in the implementation of LDPC. Okay, and what it ensures is, this quantizer, it ensures that the same transport block size is generated for small variations in allocated REs. What does this mean? Okay, let's say like you transmitted a transport block. Okay, when there was basically receiver was not able to decode it, and then it sends an ACK. Okay, and then for the hybrid ARQ, it is this, whenever this second retransmission happens, okay, it is not guaranteed that the user will be allocated same number of resources. Okay, they can be like a slight shift, or when they can be allocated little more or little lesser than what they were actually allocated. Okay, right? Because it is like the retransmission is going to happen later on, and a base station might have other priorities. Okay, other priorities means what? Priorities to serve other users. Okay, and it is the same number of resources are not guaranteed, okay, to be allocated to the same user. Okay, so what this quantizer ensures is that basically it will give you the same transport block size if there is a small variation in allocated REs. Okay, right? And that's what it is. So this is basically useful for retransmission on a different set of resources other than the initial transmission. Okay, and the reason for that I just explained. Okay, so now these are the two jobs of this quantizer. Okay, now I'll give you an example to first see how this intermediate number of bits are generated, and then I'll show you the recipe of how this quantizer actually works. Okay, so and this has been our running PDSCH example. And what is our example? We take 70 resource blocks, and with MCS of 16, that essentially is a code rate of 658 by 1024. Okay, right? And then it led to a transport block size of 28168 bits. Okay, we assume that it was given to us by Genie. Okay, I'll show you how it is actually generated today. Okay, so let's see that. Okay, for this. These many PRBs, okay, with this MCS, okay, so how will it lead to this 28168 bit block size, bit transport block size? Okay, so the number of resource elements for these many PRBs, okay, so number of resource elements available to transmit PDSCH in a PRB, okay, with these resource block is how much? Okay, I'm calculating this, right? Okay, n dash RE, okay, number of resource element, 12 into n symbol slot. Okay, what is this 12? Number of resource element in one PRB. Okay, and over how many slot this PRB is allocated. Okay, then this is basically the time duration, right? Okay, it could be one symbol and it could be 14 symbols. Okay, right? And what is this? N PRB DMRS. Okay, so the number of pilot signals which are transmitted in a PRB. Okay, so wherever these pilot signals, okay, are transmitted, you cannot transmit the data. Okay, and this DMRS is basically demodulation reference signal. Okay, so these many resource elements are reserved for sending this pilot signal, which is named as demodulation reference signal. Okay, fine. And this is NPRB overhead What does this overhead means? There are certain additional control signals which could be transmitted in a particular PRP. Okay, right? So it will come later towards the end of the course, whereas there are certain broadcast signals which need to be transmitted. Okay, and it is not necessary that they will be transmitted in this PRE, these PRBs. Okay, but if they are transmitted, then overhead needs to be set aside for transmitting those control signals as well, right? I'm just giving an example, okay, that there will be like other kind of overhead which the standard defines, okay, which could basically be used for transmitting this, which could be used in this PRP, and then this overhead needs to be set aside. Okay, so what is this? So we assume this to be 0. Okay, so you see this. What are we assuming? That this user has been allocated certain number of symbols in a slot, and then that is 14. Okay, so 12 into 14 symbols are allocated. Then how many PRBs are set aside for DMRS? This is 6. Okay, and the overhead is basically 0. Okay, so you get 162. These are N-REs. Okay, right? And then the total number of available REs over all PRBs is basically this is our one PRB, right? And it is basically, so how many total number of REs are available for the PDSCH to be transmitted is given as minimum of 156, N-RE, okay, right? So into this number of PRBs, okay, number of PRBs is how many PRBs are allocated for this user, okay, and look at this 156, N-RE. So if you look at the way we have calculated, okay, this 156, 162, okay, then how many PRBs it will be? Minimum of 156, 162 will lead to 156. And why 156? There are certain additional resource elements which are again reserved for transmitting some overhead. Okay, so that's why the minimum will always be 156. Okay, right? And if the overhead basically goes below 156, that's not allowed. Okay, so in each PRB, okay, right, over basically these many symbols, the minimum is what is allowed is 156. Okay, and how many PRBs are allocated? 70 PRBs. So 156 into 70, you get 10920. Okay, so these many resource elements are available for the transmission of this transport block. Okay, right? So, and there is one more factor which has to play a role. What is this? This is the MCS. Okay, so with this NRE, okay, we have to generate this intermediate number of information bits. Okay, and what are these intermediate number of information bits? NRE, right? Okay, correct. This is the number of resource elements which is available. What is Q of M? Q of M is the modulation order. Okay, right, and R is the rate, and nu is the number of layers. Okay, so what is happening? So number of resource elements, and how many QM, the modulation orders means what? It is the number of bit you can transmit on each resource element. Okay, correct. This nu is number of layer is 1. Why are we multiplying it by 6? This rate, basically what are we saying? Okay, that this, if let's say if the rate is 1, okay, correct, what are we doing? You are transmitting, you are not appending any parity bit. Okay, if the rate is basically lower than 1, you need to accordingly reduce the number of data payload bits which you can transmit. Okay, right? If basically the rate is, let's say, so what are we doing? This is the number of bits you can actually transmit, 10920 into 4, okay, into 1, okay, right? These bits you can transmit, but out of that, right, that is, if you look at the rate, 658 by 1024, okay, right? So what is it saying? That you will have to, out of 1024 bit, you can only transmit basically the data payload can only be 658. Rest of them, okay, will have to be the 1 minus this will have to be the parity bits. Okay, so you are accordingly reducing the data payload. Okay, and this is the rate. Okay, this is the rate with which you are multiplying, so that the data payload gets reduced accordingly. Okay, right, and this is the number of information bit 28067.8125. Okay, so you see this this is coming close to whatever we were using, okay, because we have still not applied quantizer onto it, right. So this is now this information bit will be sent to the quantizer, okay. So this is nu is the number of MIMO layers, okay, and then this value needs to be sent to the quantizer, okay, and the quantizer I will only show you, give you a brief overview of how this quantizer works, okay, and then we'll it's a very detailed procedure, okay. So we'll just look at it very briefly, and then this will help us in understanding how these objectives of the quantizers are met. Okay. So this final transport size is calculated using the next this quantizer algorithm. Okay. You see this, okay. So that I am just showing you so that we basically see how it is implemented. Okay. I am not going to go into the detail because all those details are not relevant. It is basically just to show you that those two objectives are basically met by implementing this quantizer. Okay. So what are we showing here? This is the number of information bits which we just calculated, the intermediate number of information bits. Okay. And if the information bit is less than 3834, you follow this formula. It is basically the quantize accordingly. Okay. And if the number of information bit is greater than 3834, you quantize accordingly. Okay. Right. And so in our case, basically the quantizer will follow this route, okay, and it is going to give you, by looking the number which we just calculated, it is going to give you a byte aligned size of the transfer. It will give you a number, okay, which will help in LDPC implementation by generating the byte aligned code block sizes. Okay, right. So this is you follow this route. If n info is greater than 3834, if n info is less than 3834, you follow this route. Okay, and at the end of it, this is all these details how they are developed. Okay, not relevant for this class, but what it tells us is at the end of it, the two objectives of the quantizer will be met. Okay, right, and it will give us that particular block size 28168, which from this number it is close to that. Okay, the quantizer will work on it and is going to give us this particular transfer block size. Okay, and if you see this, what is it function of? It is basically a function of the resources allocated. Okay, and this is the overhead, right? And basically, so this is what it tells us, that the number of resources, you first calculate the number of resources, then you incorporate the rate information and the modulation order, which gives you the actual number of data payload bits which can be transmitted on the resources allocated to this. So this was the second gap in our understanding, the calculation of the transfer block size. We have done that also. So what we have done in this class is basically understanding the scrambler part, and then that we have calculated the transfer block also. Okay. So I'll stop here in this class, and then we'll cover something new in the next class, which is I'll teach you in the coming class. Okay. Thank you.